Okay, the record is now on, so we can go back to the example. I don't have much more. In fact, I only have one left. Here, okay. If you can recall, this is the example that we did with the slope deflection in set 1. I think it's example this one. Yeah, it's example 7. So to make a good comparison, I'm going to use the same span length, which is 6 meters, and same load, which is 1 ton per meter for this one. Okay. So the uniform load W is going to be 1 ton per meter, and the span length here will be 6 meters. Okay, so from the previous example, we already know that the fixed end moment is -3. You see that? There, this is from your previous example, so there's no need to panic. So let's give it some names. As usual, maybe A, B, C, D, and E, so that I can say FEM AB is equal to FEM BC equal to FEM CD, that is -3 ton meter, and then that's equal to let's say FEM BA is equal to FEM CB, and it is equal to FEM. We don't need DC, right? Because it's a goes beyond the line of symmetry. So let's erase that. That's 3 ton meter. Okay, keep in mind that your line of symmetry is here. And if we are going to take advantage of this, you should sense that we are going to do only a job on 2 spans, either on the left or on the right. And we also have this as a simple end support as well. So let's, without further ado, let's take a look at the relative stiffness. Okay, now we have because it's 4i, so KAB is K, and then KBC is 4K. All right, so with modification, this, let's use pink so that you know, after the modification, this becomes 0.75K. Okay, so the second step is the distribution factors. Now we have the distribution factor BA, that's going to be 0.75 over 4.75, and DF BC, that's going to be 4 over 4.75. Okay, and because the modification here, this is the even number of span, so now you know K modify is equal to K, right? Very simple, right? So that means DF for CB is going to be equal to DF for CD, that's 0.5. Okay, so now we can begin. Oh. And we are going to take advantage of symmetry. That means we want to have of the structure. Okay, so now again, the distribution factor here is 1 because it's a simple n. Here that will be It's very long to write. So let me find the number. Only 1.158. Can we, oh, we cannot squeeze it there. So I'm just gonna write 0.16, okay? And that means this is 0.84. Kind of small, isn't it? It's 0.5. Okay. See, notice how member AB almost doesn't help at all because, you know, its moment of inertia is 4 times less, and it also has a simple end support. So, okay, we begin with -3 here, +3, -3, and then +3. But you also know that, say, on the opposite side here is -3. Correct? So now, without further ado, we are going to balance the moment. Okay? And that is 3. That's it. End of the first cycle, because the rest just cancel each other out due to symmetry. So that's the end of the first cycle. Right? So this guy got distributed here. Right? That's 1.5. And we need -1.5 to balance this. 16% only is going to come from member AB. That is about -0.237. And this is -1.263. That's it. The second cycle. Okay, and now because this is a simple n on the left, so we don't do this. We don't bring it back. Okay, we bring this to this. Okay, and that is going to be -0.631. Then because of symmetry, you know, if there is anything coming from the right, it's going to be equal and opposite. Right? So that means that's the end of our. Like that. That's it. End of everything. And because you modify this, so you don't bring 0.631 back to B either. Okay, so that means, to summarize, that's 0. This is 4.5 minus that. So you get 4.263. That is -4.263. This is too small, so it's 2.369. And on the opposite side should be minus this. Okay, so that's it. These are our answers. So let us go back to example number 1. So remember the numbers. Hey, you like that? You see that? Exactly the same. So if you know how to modify the structure properly, this is just how much time you're going to spend doing it. Okay? And actually, there are 1 or 2 issues that I can do. Okay? And then the end of the lecture today is going to be included in your exam. Generally, there are issues where you have to take care of. First one is the non-sideway frame. It's just nothing because we don't have any sideway to contend with. And the only difference is that at this joint, there are more than 2 members. So we have the 3 distribution factors for each of them. And that's all. So it's not that big of a deal. So let's say it would not be a bad idea to give you one more example. So how's that? Like one more example maybe? But I didn't prepare that. So let's say, okay, let's give it some time to write the example. Okay, it's fixed support. Let's make it longer. Okay, fixed support on the left, and then give it support here. Okay, it should be just this long maybe. Maybe you can do a better job doing this. I have the load coming in incline like that. That's 10 meters. That's 20 meters. That's 20 meters. So we should try to draw it with a good proportion. Okay, that's 6 meters. And we have the uniform load here. 1 kilonewton per meter. Right here is 2 kilonewton per meter. The slope of the load is my favorite angle, 3, 4, 5 triangle. That's 3, 4, and load here is 50 kilonewton. Okay, and interesting thing is that, let's say, now let's give it some name, what A, B, C, and D. Support C settles 30 millimeters. Okay, so that means now in slope deflection equation, you can calculate the sine angle, right, and put the values in your equation. But here we only have numbers, so that means we have to have the formula to calculate the fixed end moment. Okay, and you can find that in the sheet that I have given you. The formula for this is going to be 6E delta over L square, right? If you can recall, fixed end moment minus 6 EI delta over L square, the formula that we used to mention in the development of a slope deflection equation. So that means I have to give you EI value. It's equal to what's my rule? 16 meters squared. Okay, so now let's say relative stiffness. Now this is to demonstrate how you can handle the settlement for the moment distribution. Okay, so here first step is the relative stiffness. So now we have KAB, that's I over 30. That's long span, right? 30 meters. KBC is I over 20. and KCD is I over 6. Okay, so that by using K equal to I over 30, that is K. That is K and a half, 1.5 K, and that is 5 K. Okay, no modification because this has neither symmetry or simple in sports. It's pretty straightforward. Q is distribution factor. Okay, so let's say DF BA, you have 1 over 2.5, that is 0.4, right? Then distribution factor BC, that's 1.5 over 2.5, which is 0.6. DF for CB, that's 1.5 over 6.5. Or yeah, or you can say 3/13. And the last one, CD, it's 5 over 6.5 or 10/13. So that's a distribution factor. Okay. So step number 3, fixed end moment. Okay, we have FEMAB. So this is like a very old trick. See the load. Now I must have told you the definition of the beam, right? At least maybe in steel design class or not, but you must have had it with say mechanics of materials class before, that bending moment, the definition of the beam and bending moment is that you must have the load that is perpendicular to the member. Okay, so the load that you must use to calculate this has to be 40, right? You must take that. It's just like we treat the incline load in structural analysis number 1. Okay, so you have to use 40 for the calculation of FEMAB. That's going to be minus 40, 10 and 20 square over 30 square. Okay, that is, why do I have numbers in this? 1600 over 9 kilonewton meter. Okay, FEMBA, that's going to be 40, 20, 10 square divided by 30 square. That is 800 over 9 kilonewton meter. And next, we have a lot of fixed end moment. FEM BC, that's going to be minus W, that's 1. L square, it's 20 square over 12, right? That's minus 800 over 3. And this is equal to minus FEMCB. And then FEMCD, it's minus 2. I have 2, and the span length is 6. 6 squared over 12. So that is minus 6 kilonewton meter, and that is minus FEMBC. Now you have settlement. So due to settlement, FEM, my E is pretty bad. B silicon prime, yeah, that's going to be minus 6 EI, so 1600. The settlement turned into meters, it's 0.03. Look like a tree. Oh, better job. Over L squared. And that is minus 7.2. Now FEMBC and CB will be equal, remember? Because let's say we have this. Now this one comes down, so it comes down like this, and your moment would want to resist the settlement, so they all go in the same direction. Whether it's positive or negative, you have to see how your member moves. Now this point C comes down, so your member BC is like this. You will have the negative moment, whereas for member CD is like this. Right? So for member CD, it will be positive. Can you see that? So for CD, prime, this is going to be 1600 multiplied by 0.03 divided by 6 squared. I've got the unit, kilonewton meter. Here is 80 kilonewton meter. Why it is larger? Because member CD is shorter and therefore it's stiffer. So to cause it to settle down would mean that it has a lot of moment in it. Okay. So that's the important part that I want to show you. Okay. So now the rest is usual, nothing fancy about it. Just set up the distribution. Okay. And now we have the fixed support again. So no distribution factor here, 0, because it's already fixed. This becomes 0.4. That becomes 0.6. This is 3/13. 10/13. And this is 0. And now we have the that is minus 1600 over 9. This is 800 over 9. For this value, oh, that doesn't look like a 9. For this value at BC, there are 2 that you must combine now. That is 100 over 3 and minus 7.2, okay? Don't forget that. So that becomes minus 40.53 and 26.13 Here is 74. And here is 86. So, and the rest will be just as before. But since we have plenty of time, so I can do something for you, okay? Now here we need to balance the total of, I don't know, 800 over 9. Minus 40.53, so that is 48 something, so we need minus 48 and minus 19.34 going to come from that, and this is minus 29.01. Here is about 100 something, and minus 23.11 is going to come from that. And here is minus 77.03. So that's the end of your first cycle, as usual. Okay. Now you carry over. Here's minus 9.67. This guy comes here. Minus 14.5. This guy comes here. That's minus 11.56. This guy goes here into the fixed, minus 0.38.52. And, you know, it's just a repetition of what we have done up to this point so far. It's not really useful to see me do it. You need to practice yourself. I may leave it for you to do it from now on, or I can just carry on. What do you think? Hey. Hello? Would you like to try to complete this yourself? Unbelievable. No response. So let me do it maybe one more cycle for demonstration. That is 4.62 and it's 6.94. It's 3.35. Here is 11.15. Okay, so that's the end of the second cycle. Remember, you can always check that each cycle, the summation has to be 0, and the left and the right must be always equal and opposite in each cycle, so that in the end, when you summarize the numbers, all the final answers are like that as well. Okay, so this comes here, and so on and so forth. Okay, this goes there, goes there, goes there. Okay, seems to me that the color would help a great deal, right? 1.68, 3.47, so the 5.58, that 2.31. Perhaps one more cycle would do. Okay, so here is minus 0.67, minus 1.01, minus 0.8, minus 2.67. So that will balance that. So that's the end of another cycle. And always remember, you can check your calculation in case something goes wrong. Distribute it there and here and here. So we get the minus 0.34, minus 0.4, minus 0.5. This is minus 1.34. Okay, this number is pretty low already. So But remember, every time you carry the moment over, you must balance it. Otherwise, you will not get the answer, correct? Because you see, first cycle is perfectly balanced. Summation of moment at one cycle, at this cycle is 0. Summation of the second cycle is 0. Third cycle is 0. And now you have the new number. So if you distribute, you don't have a choice but to balance it. And here is 0.16, 0.24. Right here is 0.12 and 0.38. So I'd say that that's enough. Okay, you can sum the numbers now. This becomes minus 185.5. I should say, you know, number is large, so it's minus 186. This is 73.7 minus 73.7 minus 5.8. 5.8, and here is 51.7. So that's it. Now you can carry on and perform the calculation for free body diagram, shear force diagram, and bending moment diagram. And say you may find your diagrams funny in this case, depending on the effect of the settlement. Okay. This is the settlement, it gives you the funny direction for the moment, because it's not what we want to occur. Anyway, so that's it. We have one more example about the here, the non-size wave frame, but it's part of the frame now. I don't give the frame answer in the midterm exam, so I don't know why I should do this problem. So let's just skip it. So instead, I give you this example, which is more useful because now you know how to calculate the moment due to settlement. Okay. Now today we also have the example of how to handle the symmetry and simple end support. Make sure you know how to do this because it saves a lot of time. And you know me, I think this is the most common cases that you find out in the real world, the symmetry and stuff. So to be able to work as engineers in the real world, you should be able to do quick approximation of the symmetric situation. So in the past few years, if not many, I have always given the exam about symmetry. And many students, after learning how to do moment distribution, will refuse to learn the new things. So they stick to the old method, which, as you know, you may be able to do it. You are still able to do it, but it takes much longer and they manage to mess up. And what I have to say I dislike the most is that you see the symmetry, but you don't realize that your answers must be in symmetric fashion as well. When you get the numbers that look funny, that's not equal and opposite. Some just carry on without knowing anything, which is really, I don't know, it's upsetting. Okay, so that's it for today before the midterm exam. So let me pause the record so that it doesn't go too long.